Welcome to Team 18's glider report for AE-1601. To culminate and conclude our semester in AE-1601, we were presented with a glider project, where we were told to utilize the knowledge gained throughout the course and tasked with designing, building, and flight testing a glider. And we were also challenged with a limited balsa wood supply. The requirements for this project include that our design must have some resemblance of a glider, our glider must fit within a 16 by 16 inch box, and it also must remain intact or in one piece throughout the flight. No external assistance or remote control is allowed. No built-in propulsion system is allowed, so our glider must be drawn by hand only. Our glider must be made primarily out of balsa wood. No sharp points or edges may be present on our design, and that our glider must fly or glide a minimum distance of 20 feet, where forward distance are measured only. Here are design alternatives for wing shape. For our glider, we wanted to maximize low drag and good stability, so we decided between a rectangular wing and a tapered wing, and here are the pros and cons for each. By combining elements from both a rectangular wing design and a tapered wing design, and also through additional computational testing and multiple flight tests, we were able to create a wing design in which we felt had the highest probability of success. A wing that had a tapered leading edge and a straight trailing edge, which had pros of efficient lift distribution and less drag, but we also understood that it would be much harder to develop. Here are design alternatives for adhesives. We wanted to prioritize and have an adhesive that promoted great strength and ease of use. Here are the pros and cons for hot glue, super glue, and masking tape. From multiple flight tests, super glue showed the highest probability of success. It securely held the glider together throughout our testing while having minimal impact on drag and flight performance. Here are design alternatives for our materials. We wanted to prioritize a material that had low impact on weight and low impact on induced drag felt by our system. Here are the pros and cons for our balsa wood, cardboard, and Play-Doh. In the end, we chose balsa wood as our material. From repeated flight testing, we found that the balsa wood had the highest probability of success, and that the lightweight and low induced drag qualities of the balsa wood outweighed its negatives. In the sizing of our glider, we researched that a longer wingspan would equate to a higher aspect ratio, meaning our glider would feel a reduced amount of induced drag force, which is something we want. We decided our wingspan to be approximately 9 inches, with the root chord being around 2 inches, while the tip chord is around 0.8 inches. A fuselage length of 7.9 inches, which you can see us cutting on our right. And a stabilizer wingspan of around 2.9 inches, with a root chord of 1.4 inches and a tip chord of 0.6 inches. Here are our selections for our initial concept and design. For our initial glider design, we chose balsa wood for our fuselage, as it was a durable material which could withstand numerous flight tests. We decided to use cardboard for our wings and stabilizers, as we needed the durability and expendability of the cardboard to help us progress through flight testing, without the worry of us wasting any of our balsa wood. We decided to go with a tapered wing design that had a straight trailing edge and a tapered leading edge, as the wing design would promote lift and help us reduce our drag felt by our glider. And for our adhesive for our initial concept, we decided to use super glue, as it provided strength and structural support needed to keep our glider in one piece throughout testing.
So for testing and design iterations, at first we tested 4 grams of Play-Doh on the tip of the fuselage, which caused the glider to stall, and sometimes it would flip because the glider would tip backwards because the center of mass was too far back. Play-Doh and bolts at the frontmost portion of the wings at 12.5 grams. It did work much better, and it did change the center of mass to be more towards the front of the wings, about like at the quarter chord. It did work much better, but it didn't necessarily glide, and it did cause some issues. Plummet down to the ground, as you can see in a second. Then we removed some of the Play-Doh and went down to 8.2 grams, still at the frontmost portion of the wings, and it did go much better and did glide. Originally believed that this would be our final design, and it did go 20 plus feet occasionally. We assumed that the issues that caused it to go less than 20 feet were actually related to angle of attack and velocity. So the final design, how we changed our original design was that we originally believed we would stick with the 8.2 grams at the front of the wing, but we spoke to some mentors at the AMS, and they reminded us about torque and how distance is better and causes more of an effect on the force of the center of gravity. And we changed the mass to be positioned at the front of the fuselage. So 2.4 grams of Play-Doh and 4.5 grams from just one bolt alone. for a total of 6.9 grams, which was less than the 8.2 grams at the front of the wing, but it was further from the wing, so it caused a greater impact on the CG. So when balancing, it resulted in the CG being around a quarter behind the tip of the wing, so right on the quarter cord. And it did fly much smoother and consistently went over 20 feet and completed all requirements successfully. So balancing our glider, like I said in the previous slide, we balanced it by placing the mass on the tip of the fuselage, and the center of gravity was even with to a little bit behind the quarter cord of the wing. And then estimation of lift and drag coefficients, I started off by doing the coefficient of lift, which is 2 pi times the angle of attack in radians, which I got from the video, and putting a protractor over like a screenshot of the angle of attack that I flew our glider with. And then taking the center of lift, I was able to calculate taking the coefficient of lift, I was able to calculate the coefficient of drag using the formula of coefficient of lift squared over pi times aspect ratio times E, which is just that constant. And I was able to get the coefficient of drag to be 0.114, etc. Here's our final design in the 16 by 16 box, and the bolt is visible in this picture, but the Play-Doh isn't. In the specific image, it was under the fuselage, and you can see the slight pink of it. So the final design flight that we flew, which was our best flight, the glider went 28 feet, and the second time the glider went 24 feet. Both times went over 20 feet, which was ideal and planned. We were glad that it went as it should have, with getting it over the bare minimum mark of 20 feet. So the summary is just basically that our project went smooth, and we had a really good understanding from the beginning about what gliders require and how to start from scratch, and being reminded of torque proved to be useful in helping to develop our glider. We were satisfied with the results from both the flights and the knowledge that the glider was able to go over 20 feet both times, which is what we predicted and what we wanted. Improvements for the future, we discussed next time, possibly making the wings angled and do research regarding optimal angles, as many classmates gliders went very far with angled wings. And then for some references, we didn't really utilize a lot of outside online references. We actually utilized more of the knowledge from mentors at the Aero Makerspace to help us throughout the process. Thank you.